On the left, a pristine, hyper-modern server rack powering up instantly. On the right, a massive utility transformer sitting inert in a muddy field. Hyperscalers have allocated over $650 billion toward AI infrastructure capex for 2026, yet less than a third of the planned 12 to 16 gigawatts of new capacity is actually under construction. The industry is tracking the wrong supply chain. Capital is flooding into GPU procurement, while the physical layer remains an afterthought. Fully permitted, fully funded hyperscale facilities are sitting idle. They have the processors, but the required electrical infrastructure is trapped in a multi-year backlog. Unpowered compute is dead capital. Capital velocity in the AI sector now depends entirely on grid access. To see the source of the delay, look at the macro view of the grid attempting to connect massive new data center campuses. You can secure high-end GPUs in weeks. But lead times for utility-scale transformers have moved from a historical 12 weeks to 160 weeks. This shaded area represents the dead zone, the multi-year window where the building is finished but remains completely unenergized. A 3-year gap between construction and revenue breaks the internal rate of return model for hyperscale developers. Legacy manufacturers have little reason to accelerate production. They hold record pricing power and secure 3-year order backlogs. The AI build-out is now a race for electrical interconnection. The context of the massive AI infrastructure boom is now shifting from clean silicon to heavy industrial foundries. Utility transformers are not commodity electronics. They require massive physical inputs of copper and specialized steel. This cross-section shows the interior of a standard transformer. It consists of heavy copper windings wrapped around a core of grain-oriented electrical steel. That steel is the primary bottleneck. GOES manufacturing is energy-intensive and limited to a very small number of mills worldwide. Specialized, aging labor is also required to hand-wind these massive cores, adding a human constraint to the material shortage. On the demand side, U.S. AI capacity is scaling from 24 gigawatts to 100 gigawatts over the next 4 years. This surge in demand is hitting the market at the same time as the EV charging rollout and the integration of renewables, all competing for the same finite supply of electrical steel. Legacy transformer designs are failing to scale alongside the simultaneous needs of the AI, automotive, and renewable energy sectors. Regional power transmission zones have become the primary bureaucratic gatekeepers for new compute. Smart infrastructure strategists do not blindly apply for grid access and wait. This chart represents the total requested load currently sitting in regional interconnection queues like PJM and ERCOT. These queues are noisy. When you apply a visual filter to remove speculative applications, a much smaller column of viable projects remains. Utilities are forcing this filtering process themselves by requiring significant upfront capital deposits to weed out indiscriminate power applications. A rigorous infrastructure audit process identifies the true timeframe for grid interconnection before ground is ever physically broken. In this constraint environment, infrastructure auditing is the primary tool to prevent capital from being trapped in a speculative queue. Many data center sites are now nearing physical completion, but lack a functioning substation. Developers face a dilemma: wait 50 weeks for a standard OEM order, or find an immediate workaround. This flowchart compares two paths. To keep projects on schedule, many operators are turning to remanufactured units. This process involves the complete disassembly, precision rewinding, retanking, and strict testing of existing equipment. Remanufactured units perform equivalent to new units, but they hit the balance sheet at 50 to 70% of the cost. Most importantly, this path compresses a 50-week lead time down to a delivery window of 4 to 6 weeks. Developers use these units for schedule-critical expansions while placing OEM orders for long-term replacements. This timeline portfolio serves as the financial bridge that prevents project schedules from collapsing under utility wait times. While remanufacturing solves the immediate timeline, advanced architectural solutions are emerging. Rebuilding old equipment does not solve the underlying mass constraints of iron core transformers. The long-term fix is the solid-state transformer. This diagram shows the physical impact of frequency. Legacy transformers require massive cores because they operate at low grid frequencies, around 60 Hz. a solid-state transformer operates at frequencies above 10 kHz, radically shrinking the magnetic core volume. The critical semiconductor enabling this high-frequency switching is high-voltage silicon carbide. Watch the circuit path. The solid-state transformer converts medium-voltage AC grid power directly to DC power, without the need for a massive steel core. The 800-volt DC output matches the exact internal power architecture required by next-generation AI GPU racks. This technology removes heavy step-down infrastructure from the equation, bypassing the GOES bottleneck. There is a trade-off. Silicon carbide manufacturing is capital-intensive and distinct from standard logic node fabrication. But solid-state transformers remove legacy iron cores from the supply chain, shifting the control point from steel foundries to advanced silicon fabrication. Advanced silicon remains tethered to the physical infrastructure of the regional power grid. The AI revolution is an energy delivery challenge. Algorithmic processing is secondary if the building is dark. This map connects the two layers. Strategic operators bridge compute to the grid through infrastructure audits, remanufactured bridging, and solid-state integration. Developers who master the utility interconnect will capture asymmetric market advantage over competitors waiting in the queue. What can be built must remain strictly accountable to what can be powered. The AI race terminates at the physical layer of the grid. Solving the power distribution problem is the only way to realize the potential of a